Hi everyone, welcome back. So this is another data analysis video, and in this video I am going to demonstrate how to conduct a one-way analysis of variance, or ANOVA. So this is really common, a inferential statistical test or null hypothesis significance test used in disciplines like psychology. And what we're doing is we're using this type of test, to compare differences between groups on a categorical independent variable, or IV, in terms of their group mean score on some scale or dependent variable. So ANOVA is what's known as an omnibus test. It allows us to compare the means of multiple groups with a single test, whilst controlling for what's known as the family-wise error rate, or the type 1 error. So that's where we think we have found a significant result when we actually haven't. Okay, so where the t-test is kind of frequently used to compare mean scores on two groups, ANOVA's often used to see if there's a difference between group means when you have 3 or more groups. You can use it for 2 groups. That's a completely valid thing to do, but often it's used when we have 3 or more groups. Okay, so because it's an omnibus test, if you get a significant ANOVA of 3 or more groups, what this tells us is that at least 2 of the groups that we're comparing, and that would be, if we wanted to look at it in a very quick and easy way, just eyeball it, that would be the groups with the lowest and the highest mean. It tells us that at least those differ significantly, but we also often have to conduct a follow-up post-hoc test to compare all pairs of groups, to see if any of the other groups differ significantly from each other in terms of their mean score on the DV. So what I'm going to do in this particular video is demonstrate a one-way ANOVA, and that's a design where we've got one independent variable with 3 or more levels, 3 or more groups, and one dependent variable. So it's the most basic design, essentially, for an ANOVA. And what I'll do is I'll simulate some made-up data. I'll demonstrate how to conduct the ANOVA using the scipy stats library, and also using statsmodels, which is another software library that's really good in Python. I'll do that where we've got data where we don't have significant differences, and also those where we do, and then I'll demonstrate how to conduct post-hoc tests to follow up when we do have a significant difference. Okay, so to get started, I'm going to import some key software libraries that would be useful in this first cell. So I'm going to import pandas as PD, numpy as NP. I'm going to import scipy.stats as stats, and matplotlib.pyplot as PLT. I'm not sure if we'll do any plotting in this, but it's available then if we need it. So first of all, what I'm going to demonstrate is we'll look at a comparison between groups where the data, there is no significant difference between the groups in the data. Okay, so I'm going to start with an example that's using simulated, completely made up data. And what we're going to do is we're going to have 5 groups, and these are these different ethnicities: Asian, Black, Mediterranean, other, and white. Completely made up, this is. And these p-values here are their proportions in the population of each of the groups. So Asian, 5% of the population; Black, 15%, etc. We're going to do a sample of 1,000, sample size of 1,000. That's what we're generating. We're creating like a random data with 1,000 data points. And I'm going to specify here just one mean and one standard deviation for all the groups, essentially. So they will differ because it's a random sample, but I'm specifying that they're all going to have a similar mean. So when we conduct the actual ANOVA, we should get a non-significant result. All I'm doing here is having kind of created these variables and created some random data, specified that the data should follow a Poisson distribution with random variables with the same sort of mean and standard deviation. All I'm doing is creating a data frame for those groups, essentially. So I don't want to say too much about this. I've kind of discussed, I've demonstrated this or a similar approach to generating, making up data in order to use to conduct analysis in other videos. I will make a series of videos about data distributions as well, and show how to generate made up or simulate data that follows different distributions, such as the Poisson that we've used here. Okay, so what we've got here is 1,000 data points. It's made up, there are 5 groups that make up the data points, and what we're going to look to see is there a significant difference between these ethnic groups, so different ethnicities, one for the 5 that we've got here, in terms of their mean voter age. So is there one ethnic group that's on average older than has an older mean kind of voter age than others within the population? There's no reason to think there would be, but this is obviously just made up data. So in order to do that on that simulated data, what I'm going to do is perform the one-way ANOVA using the scipy stats.f underscore one-way function. So it's going to do an F test, what's commonly known as ANOVA. The statistic that it returns is referred to as an F value, and it's going to do a one-way because we've only got one IV, and one DV in this case. Okay, so we're not, apologies, I'm just going to have to change something because I can see a spelling error in that cell. But okay, so I'm going to run this cell with the ANOVA, and there you see what it returns. It's really basic output that it returns, but it's the important stuff, so we can see whether these groups differ from each other in terms of the mean age of voters. And we get a test statistic of 1.77 and a p-value of 0.13. So using the normal threshold for often referred to as alpha level for a significance value when we're doing these types of null hypothesis significance tests of 0.05, what we're seeing here is this isn't a statistically significant result. So we knew that because we simulate the data in a certain way. So what that means is these groups do not significantly, the mean age of voters in each of these ethnic groups does not differ significantly. Okay, so scipy, where it says statistic here, this is the F value, and scipy stats F underscore one-way method has returned an F value and P value. We can see the F value is 1.77 and the associated P value is 0.13. So it's a non-significant ANOVA result as we expected from the way we generated the data. And that's telling us is that mean voter age doesn't differ significantly between ethnic groups in the sample that we have simulated up here. So that's a non-significant result. An alternative way to run this ANOVA is using statsmodels. The statsmodels library is really good, and it allows us to specify our models, our statistical models, using formulas that are commonly used in the R programming language. Okay, so what I'm going to do here is run that same test again. We'll get the same result, but just demonstrate a different way to do that by using statsmodels. So I'm going to import statsmodels.api as SM. So I'm abbreviating it, giving it the nickname SM. And then from statsmodels.formula.api, I'm going to import OLS, and that stands for ordinary least squares. So the ANOVA model, although we're looking at differences between groups, it is a special case really of the general linear model, essentially of the type used in regression. Okay, so I'm going to run a one-way ANOVA using formula syntax similar to that you find that's used when you run this type of analysis using the R programming language. And this is formatted in the same way as a linear model. Okay, so I'm going to create an object called model and set that equal to, and I'm going to use this OLS method that we imported. OLS, and then in brackets, what I'm going to do is between quotes, so it's a string object, I'm going to specify what the DV is as a function of the independent variable. So remember what we're predicting here is where ethnicity group is our independent variable, and we're using that to predict age, to look at differences between those groups in terms of their age. So age is the DV essentially. So the DV goes first, then you have this tilde character, which you could read as is a function of essentially. So age is a function of ethnicity. Okay, so this is just a way to specify a linear formula, and you'll see when we do linear regression using stats models, we could if we were using an ANOVA here with more than one IV, we could just add that into this equation. So we'd ethnicity plus independent variable 2, whatever that was. And I'm specifying here the data is the voter frame. So voter frame is this is this object, the pandas data frame that we created there. So essentially, I've created this object using the OLS method from stats models. I've told it the formula to use, I've told it the data to use, and then you have to put this dot fit at the end. Okay, so I've put dot fit, and that's going to fit the model. And then what we're going to do with our model object is then use that in a kind of ANOVA, a specific ANOVA method from stats models. So I'm going to create another object here called ANOVA underscore res. So that's the name I've given it. So it's ANOVA results essentially, and that's going to be sm stats models dot stats dot ANOVA underscore lm. So the method that we're going to use here, having fitted a linear model here to analyze it, is the ANOVA linear model method. And the things I'm passing to it as arguments, as parameters, are model, which is this linear model that we fitted with these parameters, this data. And I'm specifying that we're going to use typ equals 2 is, I'm specifying we're going to use type 2 sum of squares. Okay, I don't want to say too much about the different types of sum of squares because it'd be a bit too much of a digression. But it basically, there are type 1, type 2, type 3, and they differ in terms of the way that variation is assigned to variables essentially. In this case, for a one-way ANOVA, type 2 is absolutely fine. And then I'm using a print statement. I'm just going to print the results ANOVA res. And if I run that, what you see we get a table which shows us our factor, which was our independent variable ethnicity, shows us the sums of squares, the residual sum of squares, and the factor sum of squares, degrees of freedom, our f value, and the probability. So what we can see here is we get an f value of 1.77, p value of 0.13. So that agrees with what we got from scipy above. From the stats F1-way method. So we expected the results to be the same, but that's just another way to do it. This is kind of quite nice that we're specifying, we can specify much more complex formulas here. Okay, so that's how to run a one-way ANOVA using the scipy stats library and using stats models when you don't have a significant result. Now let's change it and change that simulated data a little bit, and this time demonstrate same things but where we have a significant difference. Okay, so all I'm going to do here is change a couple of things with our simulated data. What I'm doing is I'm picking one group, the white group here, white age, and I'm giving it a different mean compared to the rest of the data frame. And then underneath, what I'm doing is I'm using numpy np.where, and everywhere in where voter ethnicity is shown as white, we're going to replace the voter age with this white age object essentially. So it's got a slightly different mean age. And what we should find is we then get a significant result. So we know at least kind of 2 of the groups differ significantly in terms of the mean age of voters. So the same 5 groups as well, same 5 ethnic groups. Let me make sure I run that cell. And then we'll use the scipy stats method, the same as above, stats.f underscore one way. And this time what I've done is I've just passed each of the groups. We saved them as specific objects here, voter age for each group, and I'm passing all 5 of them in. So if I run that, this time what we see is we again get our test statistic, our F value of 10. This time it's 10.16. We get a p-value of 4.56 times 10 times e to the negative 0.8. E to the negative 0.08. What that means is we've got a very, very small p-value, so we'd have to move this decimal point kind of 8 places to the left to make this small enough. So it's used. What's happened here is it's used scientific notation to make it as precise as it can, essentially. Otherwise, this would just be 0.0000456. But what it's telling us is we have a p-value much smaller than 0.001. Okay, so we see there's a significant difference between the ethnic groups in terms of, I'm going to have to change a few things there. Ethnicity group in terms of mean, that should say mean. Oh, sorry, I'm spotting typos and I can't just ignore them. So we now know from this there is a significant difference between some of these ethnicity groups in terms of the mean age of voters. We've got an F value of 10.16 and a p-value of less than 0.001. Let's do the same analysis using the statsmodels formula. So we've already imported statsmodels above, and we're going to do exactly the same thing as we did before. We're going to create a model object, use the OLS, ordinary least squares method, by specifying the model formula. Age is a function of ethnicity. The data we're going to use is voter frame. Remember, we've changed the voter frame so that mean age for the white group is slightly higher than the others. And then we're going to do our ANOVA results object and set that equal to statsmodels. We're using the ANOVA underscore linear model method. So let's run that. And we get the same output as above. We get an F value of 10.16. P is equal to 0.000000456, something like that. Okay, so highly significant result. When we've got a significant result, like I said at the beginning, it tells us that whichever group had the lowest mean age and whichever group had the highest mean age, those two at least differ. But where we've got 5 groups, maybe we want to know if this group and this group differ, this group and this group differ, and this group and this group differ. So we'd be making multiple comparisons, and to do that, we want to do some sort of post-hoc tests that control for the fact that we're doing multiple tests, so we don't inflate that family-wise error rate. Okay, so one manual way of conducting post-hoc tests is to kind of run multiple t-tests comparing each pair of groups, then adjust the threshold for a significance test so it's stricter, thereby controlling for the family-wise error rate. So a common method for doing this is the Bonferroni method, whereby we simply, I've got to change that as well because that's now spelled simply. Divide the normal criteria for a significant p-value by the number of comparisons we're making, and that's kind of the number of tests we're running, so the number of t-tests we do, and then use the resulting value as our new threshold for what we would accept as a significant result. So for example, if we were conducting 5 t-tests to compare different groups, we'd divide the normal alpha value of significance 0.05 by 5. So 0.05 divided by 5 would give us a new threshold of 0.01. Unless a test had a p-value of 0.01 or less, we wouldn't accept it as significant. Okay, so what I'll do here is I'll demonstrate based on this significant result we just got above here for our ethnicity age kind of data set. I'll demonstrate how to do this manually. I'll kind of create a couple of for loops that automates the tests for us, and then we'll compare each t-test against an adjusted significance value threshold. In this case, we're making 10 comparisons. So the Bonferroni correction and new level of alpha will be 0.05, our standard significance level for p-value for most tests, divided by 10, which is the number of tests we're doing. So we won't accept anything that's significant unless it is has a p-value of less than 0.005, so quite small. Okay, so quite strict. We're making it harder to find a significant result. Okay, and the reason we're doing 10 tests is because we've got these 5 groups here, and we're comparing each group with every other. So we're comparing Asian with black, Asian with Mediterranean, Asian with other, Asian with white, black with Mediterranean, black with other, black with white, Mediterranean with other, Mediterranean without white, and then other with white. So altogether we should be about 10 tests. Alright, so in this cell what I've done is I've just created it's syntax that it runs through each ethnic group, matches it with another group, and then runs a t-test. And I've done that using a couple of for loops. One is a nested for loop. So to start with what I'm doing here, where it says ethnic underscore pairs equals, and then these brackets, I'm creating an empty list, and then we're going to use this for loop to loop through each ethnic group from 0 to 4, but not including 4. We have 5 altogether. Remember, it's 0 indexed in Python, and the first value is inclusive, the last value is exclusive. It doesn't include it. Okay, so what I'm doing is for ethnicity 1 in range 4, and then a nested for loop for ethnicity 2 in range ethnicity 1 plus 1 up to 5. Ethnic pairs dot append. So it's going to pair each of them up, each ethnic group, with another, and then append them and add them into this particular list here. And then once that's done, we're going to go to this second for loop, where we're going to take each of the pairs that we've created here, and we're going to print them out so we can see which ones are being compared, and then we're going to use the statsmodels t-test underscore in for independent. So an independent samples t-test, and that'll give us the result. So it'll give us a test statistic, a t-value, and a p-value. So let's run that. And what you see is we have 10 tests, and this top one is comparing the Asian group against the black group, and looking to see if there's a significant difference in voter age. We get a t-test statistic of 0.84 if we round that to 2, and p equals 0.4, so not statistically significant. And remember, the only group that we increased the voter mean age on was the white group, so we'd expect the white group to differ from some of the others. Maybe we'll see how that works. Okay, and if we go through these, remember what we're looking for is a p-value now that is 0.005 or smaller. Okay, and what we will see is when we compare mean voter age for blacks against mean voter age against the white ethnic group, we get a p-value that is less than 0.005, and the same with Mediterranean against white and other against white. So these are significant results. So it looks like we've got 3 significant differences between the black and white voter age, Mediterranean white voter age, and other and white voter age, but not Asian and white. Although, using our traditional significance criterion, that would be 0.05, that would be significant. We could do multiple comparisons, so we've had to adjust that threshold down, make it stricter. Okay, so looking at the above list of t-tests and p-values, we see that with an adjusted level of significance, there appear to be statistically significant differences between the black age groups and the white age groups. T equal to 5.38, P is less than 0.001. Mediterranean age group and the white age group, T equals 3.52, P is equal to 0.0005. And the other and white age group, T equals 3.76, P is equal to 0.0002. So if you look at that one, 3.76, and I've rounded that. Okay, based on what we know about the mean voter age for these groups, The data was constructed so that mean age for white voters was older than the other groups. So this indicates the mean age for white voters was significantly higher than these three groups when we used the Bonferroni correction method. Okay, so Bonferroni correction is quite a conservative correction, and we may risk making a type 2 error and rejecting significant differences by using this method of post-hoc adjustment and comparison. So another method that's commonly used is the Tukey HSD, Tukey's honestly significant difference, I think it stands for. So it's less conservative or less strict than Bonferroni, and it can be implemented for pairwise comparisons using I've got to change that, sorry, using the statsmodels multiple comparisons method. Okay, so within statsmodels, there's actually a method to conduct pairwise Tukey HSD. All right, so what we need to do is import that from the statsmodels library, and it sits within a kind of a kind of catalog of methods called multiple comparisons. So from statsmodels.stats.multicomp, we're going to import pairwise Tukey HSD. And I'm creating this new object called Tukey, and I'm setting that equal to pairwise underscore Tukey HSD. So this method, and what we're passing in is ndodge equals voter age, and kind of ndodge in this case means is our dependent variable. So there's this syntax for certain where when you kind of run certain tests using statsmodels, where you can specify the exodge, usually the independent variables, and ndodge the dependent variables. So what I've done is I've set ndodge is equal to the voter age, and the groups is equal to voter ethnicity, so our independent variable in this case. And we've set our alpha value to 0.05. So this test is going to kind of adjust the criterion to make sure we're not committing a type 1 error. And what I've done underneath, you kind of don't need to do this. So this above is all we need to conduct the Tukey HSD test. But I've used the matplotlib.plot method here, and I'm going to create a forest plot so it will help us to visualize where the differences are. I think forest plots are pretty good for that. So all I'm doing is Tukey is the object we created above, so I'm going Tukey.summary. If I run that, what we will get is the statsmodels, this nice HTML table for these statsmodels multiple comparisons using the Tukey post-hoc comparisons method. And what it does is it gives us an adjusted p-value. Okay, it shows which groups it's comparing, and quite nicely it tells us whether we reject, whether it's true or false that we reject the null hypothesis. So remember when we did the Bonferroni above, we found that 3 were statistically significant. And if we look at the adjusted p-values, that was black compared to white, that's significant here. Mediterranean compared to white, that's significant here. Other compared to white, that's also significant here at the 0.05 level. Okay, and you can see that those are the 3 that have true next to them. So it's true that we reject the null hypothesis, that there is no difference between these groups. Okay, and the last thing underneath was that little bit of extra syntax that I used there to create this, what is known as a forest plot. So it shows you the mean for each group and the confidence intervals around it. I put this vertical line in so you can see sort of like it's set right at the end of the white group. Remember, this was the group we changed to make the mean age higher. And if we look, what we can see is I probably needed to change the scale on the x-axis, but you can see here where the kind of error bars overlap considerably, you're not going to get a significant difference. So none of these 4 groups were significantly different from each other, but the other group was significantly different from the white group. The Mediterranean group was significantly different from the white group. The black group was significantly different from the white group, and their error bars do not overlap at all with the white group. The Asian group wasn't significantly different from the white group, and you can see there is overlap there between those 2 groups. Okay, so What we've seen is some nice output there for the 2-key HSD comparison that was conducted. We can see the adjusted p-value for each test, and this way, in case we can interpret any test with an adjusted significance value below 0.45 as statistically significant. And we also get that nice column label there where it tells us whether we've rejected the null hypothesis or not. The null hypothesis being that the groups are not different. Note in this case that the results of the 2-key HSD test are identical to the Bonferroni method and show significant differences between the same 3 comparisons. That's not always going to be the case, as these two tests, as I said, they differ in how strict they are. 2-key is a bit less strict than Bonferroni, so it might have been the case that we saw a different result. We didn't in this case, but if that does happen, you shouldn't necessarily be surprised. But what you shouldn't really be doing is kind of doing multiple post-hoc comparisons and picking the one that gives you the results that you are most happy with. You should specify which one you're going to use beforehand and stick with that. Okay, so I'm going to stop talking now. I'm going to demonstrate some more ANOVA. I'll do some more examples of one-way ANOVA in the next few videos, and a repeat measures one-way ANOVA. I'll use some actual real data rather than just simulated data examples like we've done in this case. But hopefully that was useful. What we've done here is we've used the one-way ANOVA model. We've demonstrated how to conduct that analysis using scipy, the f_one-way method, and also using the statsmodels software library. And then we've looked at a couple of post-hoc comparisons. One I did manually, which was the Bonferroni correction, where we just did multiple t-tests and we adjusted what we'd accept as a significant t-test. And the other where we got statsmodels to do the nice 2-key HSD comparisons for us and give us a nice table. Okay, that's enough from me, I think, for now. Thanks for listening. I hope this was useful.